Hi everyone, my name is Taeyoung Kim from Seoul National University. I'll be presenting our work on multimodal grounded planning and efficient replanning for learning embodied agents with a few examples. Let's start by understanding the general process of learning embodied AI agents. Initially, we collect expert demonstrations generated through a scripted policy. Here, you can see an agent picking up a credit card and traveling around to find a tall lamp. After finding a tall lamp, it toggles it on and examines a credit card in detail. Following this, we gather human annotations for these demonstrations. As shown in the example, examine a credit card with a tall lamp. These annotations often include step-by-step instructions such as pick up a card, move forward, and toggle on a lamp, and so on. Using this annotated data, we are now ready to train an agent model through supervised learning. However, this process can be costly, both in terms of time and resources, making it difficult to collect a huge dataset. Thus, it may be difficult to collect data in a large scale. Moreover, supervised learning with only a few data points may not result in sufficient performance, motivating the need for more data-efficient approaches. Recently, several works have explored leveraging large language models for planning by using few-shot prompting. For example, these methods use linguistic common sense for generating plans. Given language instructions, an agent generates a plan with large language models and executes actions in sequence. However, neglecting the initial state of the environment can lead to inappropriate plans. Additionally, heavy reliance on large language models for closed-loop replanning results in high latency and computational cost. This brings us to our key motivation. How can we let agents to plan effectively and replan efficiently with a few examples? To address those limitations, we propose a multimodal planner that considers both environmental status and language instructions to generate long horizon plans with a few data. We also propose efficient replanner that revises misleading subgoals without large language models. We call this agent FLAIR, which stands for Fusion Language with Environmental Adaptive Replanning Embodied Agent. This is how FLAIR works. First, MMP generates initial plans with language instruction and surrounding views. As the agent receives commands, it collects surrounding views to reflect environmental status. Both language instructions and surrounding views are used to measure multimodal similarity to retrieve top K relevant training example from a few datasets. Then, it prompts LLM to generate initial plans. While executing initial plans, if the agent fails to locate a target object, it requests for replanning to EAR. Then, EAR substitutes missing objects with similar ones in the scene. EAR lists up detected objects so far and computes the semantic similarity between their class names to replace inappropriate object with most similar object detected in the scene. Here, as the garbage can having the highest similarity, it takes the place and results in grounded plan. To evaluate the effectiveness of our FLAIR agent, we used Alfred benchmark, a widely used instruction following dataset. We tested FLAIR with 4 language models to validate the compatibility, which includes both GPT models and open-source model Llama 2 and Vicuna. We first observed that using Llama 2, an underperforming language model, our agent still outperforms previous work in unseen environments. With powerful language models such as GPT-4, FLAIR significantly outperforms state-of-the-art by large margins. We now investigate the performance of the initial planner that generates action sequences denoted by static planning. We compare accuracy of our agent and recent LLM-based planning methods LLM Planner. Overall, we observed that FLAIR consistently outperforms prior work by noticeable margins in accuracy for both seen and unseen environments across the language models. In our evaluation study, We compare the result with and without MMP and EAR. As shown, removing MMP results in significant performance drops, indicating the effectiveness of our multimodal retrieved planner. Removing EAR also results in notable performance drops, indicating the effectiveness of replanning with visual cues. Here are some qualitative results. Without MMP, the agent misinterprets tasks such as incorrectly placing a soap bar in a sink basin. With MMP, the agent correctly completes the task by cleaning a soap bar in the sink. For replanning, without EAR, the agent fails to identify misleading objects. With EAR, it successfully substitutes the incorrect object, resulting in an appropriate environmental grounded plan. Our proposed flare can also be applied to robotic tasks. In this example, flare successfully rearranges objects based on instructions, while the baseline approach fails due to an ungrounded plan. You can find our code used in the experiment in the GitHub page. Also, you can find more qualitative examples in our project page. Thanks for listening.